You're doing 60 miles an hour down the highway. Suddenly, a tree branch falls right into your lane. Your foot slams the brake pedal, and the front of the car dives toward the asphalt as the tires scream. In that split second, whether you hit the obstacle or stop in time is a pure physics problem. Can your car neutralize all of its forward momentum within the shrinking distance between you and that branch? Out there in the real world, motion is chaotic and continuous. You can't pause the universe to calculate your speed, the friction of the tires, or your exact stopping distance. But on paper, we can freeze that exact sequence of events. We can translate a terrifying, messy skid into a clean, precise geometric map known as a velocity time graph. This map provides a predictive look at the physical interaction between the car and the road, turning a chaotic event into a set of measurable coordinates. To build this map, we start with two dimensions. We put velocity, how fast the car is moving, on the vertical axis, and time on the horizontal axis. Let's trace your emergency stop. For the first half second after you spot the branch, your car is still traveling at a constant speed while your brain processes the threat. Then you stomp the brake, and your speed plummets until you hit zero. The steepness of that downward line holds a crucial piece of information. In geometry, we find a line's slope by dividing the vertical drop by the horizontal run. When we divide a change in velocity by a change in time, we get meters per second. That gives us the exact rate of acceleration, or in this case, deceleration. This means the slope is a direct visual representation of force. A steeper line requires a more violent braking force, throwing you against your seatbelt. So we know the forces at play. To know if you actually hit the branch, we need to find out exactly how much physical space your car covered before coming to a halt. While division reveals force, multiplication reveals space. When you multiply velocity in meters per second by time in seconds, the time units cancel out, leaving a final result in meters, the displacement of the vehicle. This animated graph shows us exactly where that distance lives. It is the total area enclosed between the line of our motion and the bottom timeline. We can break this area down into two distinct shapes. This initial rectangle represents your thinking distance, the patch of highway you consumed while your foot was moving toward the pedal. The triangle next to it represents your braking distance, the road you chewed up while the brake pads clamped down hard on the rotors. The sum of these two-dimensional areas provides the total distance the car traversed before the tires stopped rolling. We can test these same geometric principles vertically, like riding a hydraulic elevator from the third floor down to a basement. When the elevator drops, it accelerates downward, holds a steady cruising speed for a few seconds, and then decelerates smoothly until it comes to rest at the bottom floor. This chart shows how we model that journey. We look at the area under the curve to find our displacement, breaking the complex shape into simpler parts, the rectangular region labeled A1 and the triangular region above it labeled A2. Calculating the combined area of these blocks determines the depth of the elevator shaft using the movement data of the cabin. Whether a vehicle is sliding forward on asphalt or dropping down a concrete shaft, these geometric rules act as universal constants. They can measure physical space no matter which way we're traveling. A velocity time graph acts like a two-way mirror. On one side, you have abstract lines and slopes. On the other, you have the very real physical sensations of motion. Your analytical toolkit comes down to basic arithmetic. Division uncovers the invisible forces pushing and pulling on you, while multiplication reveals the actual physical space you've consumed. We can decode these motions today thanks to the architects of classical mechanics, like Sir Isaac Newton, who first mapped out the mathematical laws governing our universe. The next time your stomach drops in an elevator, or your seatbelt locks during a sudden stop, remember that you are living inside the math. Understanding kinematics allows us to see past the messy blur of the world around us and look directly at the underlying geometry of motion.